All right, thank you. Thank you very much. And thank you everyone for your patience earlier as we made it through our technical difficulties. So, welcome to the Lower Columbia chapter and the Tualatin Historical Society meeting tonight. Tonight we are going to have Bill Burgel speaking on when Yellowstone was in Oregon. So, Bill, you are on.
Thank you, everybody. And Scott, if you're still here, I may lean on you a bit or two, but let's just say this topic is, there's a lot going on geologically with this title, okay? And I've got 45 minutes. Each of these topics that I'm going to rattle off here in a few minutes would take 45 minutes apiece. So I'm not going to do justice to some of these geologic principles, but just bear with me, jot down your questions. I think Sylvia will have some time afterwards to go through some of the questions, however Sylvia would like to do that. So I'll begin. My wife asked me to correct the title. She said when Yellowstone was in Oregon, she said the better title would be when the hotspot that formed Yellowstone was in Oregon. And you know, it's probably a loose connection between the Ice Age Flood Institute, but let's just say that Yellowstone, if you see the little graphic at the bottom of the words and the numbers, 34 million years the Yellowstone hotspot was in Oregon or California, just 14 million years in Idaho, and right now it's currently just been 3 million years in Wyoming and Montana. So we should, Rick and Sylvia, we should make a letter to the state and to Congress to make us the Yellowstone state. So that's my pitch. But these are some of the agenda. I'm going to talk about all these concepts here. I'm going to start from a time period that was 50 million years ago, okay? And got 45 minutes. And if you can see the, basically gotta get rid of this thing. All right, if you can see these geologic concepts, every one of these is basically a master's degree, okay, or even a PhD. So just know that there's a lot of stuff here. And if you wanna ask me questions afterwards, or Scott Burns, please feel free to do that. My email's at the end of the show and you can copy that and ask me or Scott any questions. But you guys all know what Yellowstone looks like, and it's very active as we speak. So lots going on in Yellowstone. We know the magma chamber is very much near the surface there. It's moving around. It's tilting the lakes. Bob Smith at University of Utah measures the lake tilt and knows that this place is still hot because things are moving just under the surface there. The black line around there shows the size of the caldera, quite big. It's 45, 50 miles across by 35 miles wide. Similar to one that's here in Oregon, but we'll get to that in a minute. And here's a sketch of the magma chamber as this North American plate's going from east to west or from the right to the left on the screen. And the hotspot is basically heating this area up here where it says Yellowstone caldera. So that's what's going on in Yellowstone. But the idea of a hotspot, I'm going to just touch on that because it's pretty elementary, but it is kind of a key thing that really started the whole concept of continental drift seafloor spreading, which turned into plate tectonics. Now, this gentleman, J. Tusa Wilson in '63, came up with this concept based on the Hawaiian Islands. And Tusa Wilson was very much a naysayer. Scott talked a little bit about Brett's. This Tusa Wilson was one of those naysayers. He didn't believe in anything continental drift, and then he basically immersed himself in the data, and over time, he became a big proponent of plate tectonics. And it was basically this concept about the hotspots and moving a lithosphere over a hotspot. And this is a diagram what he used. And basically you've got a hotspot coming, not 100%, all the geologists know how these things originate and where they come from. Maybe we can dig into that, but basically as this plume reaches the surface and these plates are convecting over the top of that, you'll see different, basically the magma will move to the surface and create an island. The weight of this fairly big edifice will start to sink once the source is removed. And as long as the heat's there, these things will grow and stay above the surface of the water. And then what happens is the plate moves on, these cool, the heat's no longer there to buoy it up. They get to the level of the earth, of the ocean, and the ocean will cut the top of these mountains off, and they're called seamounts or guyots, G-U-Y-O-T, and then they'll continue on west in this case. And here's a case, basically it's roughly 60 million years of seamounts that basically extend west and then north from Hawaii. And you can see the million years is basically what these numbers represent when these seamounts were formed. As you know, the one in Kilauea is active today. 44 hotspots throughout the world. They are responsible for what geologists are calling large igneous provinces, such as we have here in the Columbia River basalts, and then, as you know, in Hawaii, Galapagos, that sort of thing. Iceland is also a hotspot on a spreading ridge. That's what we know in terms of that goes. But in terms of Iceland, we have another concept. The next concept is this terrain accretion, which the hotspot that's creating Iceland is basically used as an analogy, an analog to what we call Celestia off the coast of Oregon about 51 million years ago. I say 50 million years ago. It was roughly off the coast. And this Iceland-like basaltic province basically was being moved into this gap that existed between what is now California and the state of Washington. So we have these lineaments that we geologists can trace. And here comes this piece of Iceland coming in, a basaltic province, a large igneous province, as Nick shows you on some of his sketches here. And you'll see he's got Iceland over in the corner here. But basically that hotspot, which, you know, again, that's how Yellowstone formed. It formed this island similar in shape to Iceland, and as it slammed onto the US coast, it smeared all along based on the momentum and the direction of the plate tectonics at the time. And you can see it's basically, right now you can see it, the stippled area is what we still recognize as Celestia. So that's underneath the Columbia River basalts, and then Troutdale Formation, and then we get on top of all that is the Missoula flood deposits. So that's all still here, right underneath our feet. And anytime you go kayaking on the Willamette River, if you go down by Elk Rock, just south of, to my back is the boat ramp there at Milwaukee, and I'm going over towards Lake Oswego. So this is Elk Rock, Highway 43 is on top of here. But all this, this is all this basalt from Celestia. You want to call it Iceland, you want to call it generated by Yellowstone, but it's all the basalt that came from this accreted terrain, which we call Celestia. Here's basically this basalt of Waverly Heights is the technical name for it. And this area is where I just showed you when we were kayaking through, basically this kind of this tannish color, and you see there's quite a bit of it in the area here, this basalt of Waverly Heights, and a little spot over here by 17th as well. So email me and we can go on a tour and show you this old rock. But basically when Celestia did dock, again, there was a subducting plate that was bringing it into the North American plate. And when that happened, basically it jammed up the trench in which these plates were subducting, and suddenly that broke off and then started a second subducting plate. And this one later caused the Western Cascades about 40 million years ago. Again, this thing docked around 50, and then the Western Cascades started bubbling up about 40 million years ago. And I'm sorry if I've lost you, but just bear with me. It gets a little more colorful as we get going here. A couple of other screenshots of what the Celestia looks like. It slams in there. Again, just one subduction zone plate. It's a Farallon plate. And as it continues to subduct under, you'll see there's two subducting zones. One is now rendered inactive, but the plate still exists. It's still floundering around down there. And here comes this second plate. So this is a fairly complicated geology, and we're still trying to figure this part of the puzzle out to this day. Talked about that, but now that we've got the hotspot, the Yellowstone hotspot docked right here in Portland, so it's here, not quite in Oregon. You see this hand sketch, we've got the future state line up north on California. This is down around Mendocino. California is where basically this initial docking occurred, and we'll get it up into Oregon here sooner or later, but for right now, let's just assume this is where we're at, and you got the hotspot coming in. You got North America moving from east to west, and here's basically the approximate coastline background. This is 50 million years ago, okay? All right, so we're gonna start moving, but now that you've basically the hotspot is pretty much, they're considered semi-permanent down in the mantle. And if that stays pretty much where it is, and the plate, the North America plate moves from east to west, the hotspot's gonna then migrate just like it does in Hawaii. So that's kind of what's going on in terms of, there's some talk about, you know, the warm springs at Canada, the hot water that's generated down in the subsurface there may be the result of one of these ancient Yellowstone locations. But it continues, the plate continues to move east to west. We're now getting a little further. This track of these hotspots are continuing in a fairly straight line, and pretty much again like what happened in Hawaii. So you get these episodic places. What happens on these mantle plumes is they create a conduit, and they kind of tend to stay in that conduit until they move off. So you'll get a lot of leakages as these things go off, and that's similar to what we get with the boring lavas, but that's another subject too. So it continues to about 29 million years ago, and that's basically when a fairly large volcano erupted, and we're calling that now the Smith Rocks area. We're calling it the Crooked River caldera, and that was very active 29 million years ago. And we're calling that a supervolcano, which is another concept that you can take at geology class. But again, you've got this supervolcano. Again, the caldera was similar in size to what's there in Yellowstone. And this is basically what Jason McConaughey at I didn't say his name right, but at Dogami, he's working on this. I think Kerry Gordon as well has worked on this. But you see the caldera is over here in this area, and basically it occupies a good portion of Central Oregon. That the red is what that initial Crooked River caldera is located. So Smith Rocks, as you know, is a lot of this rhyolitic tuff. great for climbing. and then you have another example of that to the east, but we'll talk about that in a minute. But you got this, yellowish tuff that is evident there in the Smith Rocks area, which is very similar to the word Yellowstone and these rhyolitic. These are, excuse me. These are basically hydrolyzed by the sulfuric acid to turn yellow, but you do have this same kind of rock type in the Smith Rocks area. You also have the hydrothermal deposits that are evident in the Smith Rocks area as well. All right, so now we're 23 million years ago, and the hotspot continues to migrate to the east. Let me rephrase that. The hotspot doesn't move. The continental plate moves to the west, so the apparent motion is to the east. So now what happens, we've got something called the northwest clockwise rotation, and that's basically what is creating that extension and this rotation is the fact that the Farallon plate, basically the spreading center got overrun, and the spreading center got converted into about 20 million years ago into a transform fault, which is a precursor to the San Andreas fault. So this motion is fairly strong in terms of creating a significant amount of dragging the whole western part of the North American plate to the north. At the same time, it's moving east. It's basically, you can see this torque on this plate. This is the Pacific plate now, and this is the North American plate. And this conversion from a spreading center to a transform fault, which is like the San Andreas fault, I just wanted to show you that's kind of what it looks like. You have this opening up, and if you take the whole western part of the US and kind of rotate it to the west and the north, you get kind of an extension throughout Nevada. You can see the spines of all the mountain ranges that look like caterpillars moving from south to north or north to south in that area. Again, a couple more shots of this rotation vectors. And you also have rotating blocks of this, the Klamath Range and then the Blue Mountains as well. With the apparent spreading center located, the rotation center located near Pendleton, Oregon. Another thing, we can change the city charter there at Pendleton and say the center of the universe. Another shot that shows you the apparent rates that these plates are moving. We're 1 millimeter a year. It's pretty tiny, but still, it's as you go further out on the plate, the more rotation you get. We talked a little bit about this old subduction, new subduction. These slides don't quite show it, but again, you've got a hotspot out here, and you got the you've got the old plate through here. So if you can imagine the hotspot being about where the cursor is, if the hotspot stays in one place and this relic, this old Farallon plate is sitting down there, sooner or later it's going to have to burn through that plate. And that's kind of what these things that happen, what we call slab failure. Again, I told you this is a master's or PhD level class, but you end up with this hotspot plume burning through the remnant of the plate down there, and the hotspot will heat the plate up and then finally burn through it. And that's kind of all happened here. And now I'll show you this picture too. It tries to show you how that works and how you can get some extension in a compressional regime. But this is basically, you get the pulling apart of the area, so you get some tension in there. But you also get, more importantly, you get this backflow of there's a hot spot here, and you get the Columbia basalts that start coming up in that same area. So you've got this trend where you've got this, you've burned through the plate, so you got some momentum of the magma back towards, the bend area. So you got the high plains trend, and then you also got the Yellowstone trend headed east. So I'm just going to jump through that, and we can talk about that a little later. It's very difficult concept, again, because it's underground. It's hard to see, of course, but this is our best guess why everything kind of hit the fan, so to speak, in southeast Oregon about 16 million years ago. I mentioned the northwest rotation, but you'll see that we've got this rotation started, and you'll see that here's the future border of Oregon and California. And now you've got a couple of these hotspots, these dormant hotspots have moved up into Oregon by this northwest rotation. And that's going to continue. You can see here's the border, and these hotspots are now working up into the Portland area, so to speak. So they've got a ways to go yet, but 15 million years ago, these dormant hotspots are now moving up into the state of Oregon. Again, you still have the plume moving to the plume's not moving, but the plate's moving to the west, and so the relative motion is you got this eastward hotspot activity. There's another shot of all the chaos that ensued in the geologic world once the hotspot burned through the Farallon plate. And I'm not going to go into that, but basically there's a lot going on in this slide because of what's going on in southeast Oregon right there. The key thing is the activity, the melt of that plate through there, and the hotspots spread up through the Columbia basalts. It started down here by the Steens, worked it up into the Picture Gorge and Imnaha, and then some of these flows, the whole thing youngs from south to north. All these Yellowstone, the Yellowstone hotspots down in this area, but all the Columbia River basalts all young from down. This is the oldest down here, and the youngest up here as it migrates north. And the hotspots continue to the east, and these are the relative ages of these hotspots as they show on the terrain. Yeah, I'll just skip through those. But these are just the spread of the flood basalts from, again, they emanate from southeast Oregon up into the state of Washington is how these things flow. You also have something called bimodal volcanism going on, and so I'm just going to skip through this, but just suffice it to say that you can get basalt out of these this magma chamber, but you can also get a more felsic magma, which is rhyolite, that comes out of these as well. And I'll skip over the process here, but just know that that's going on as well as this Yellowstone goes through. And a function of that is the thicker your continental crust is, the more likely it is to produce rhyolite as these hotspots move across the terrain. Again, here's Leslie Gulch, 15 million years ago, mostly rhyolitic, as was Smith Rocks. And now we're getting into the state of Idaho with the hotspot, and this is one of the largest super volcanoes in the world. It's what they call a volcanic explosive index of 8, which is right up there in terms of its explosivity. There's 30 feet of ash up by Pasco, up by Yakima, that Nick talks about, but then you have quite a bit of ash over that buried a bunch of ancient rhinoceroses about 10 million years ago over in the ashfall beds in Nebraska. So this is the old track, how it used to be, but as you know, this thing is now shifted to the north by the northwest rotation. And now we're getting into Yellowstone proper. And these calderas are pretty well defined in the literature and by scientists working in the area. And you're continuing to move about 8 million years. And again, when you had this plume, it was quite high and it affected all the, this is about 7,000, 8,000 feet of elevation here. And all the river drainages all shifted around this localized hotspot as it moved towards Yellowstone. And then it finally got into the Yellowstone area about 2 million years ago. It had a super volcanic eruption. Again, one of a VEI of 8. So that was created all of what they call the Huckleberry Tuff, which surrounds this whole area in terms of recent activity. So this again, this is a cartoon cutout I did on my kitchen table, but this is again why I say this is fairly master's level geology, and just to explain how Yellowstone ended up. You see the hotspot's now up in Portland here where it belongs. And you have Smith Rocks over there where it belongs. Another picture of the way all these numbers are the million years ago. Again, everything all broke loose 16 million years ago when it burned through the plate, or the subducting, the relics subducting slab that was under the mantle. I talked about the movement of this. The hotspot creates a local high, and you can see once the pulse moves through, very similar to like what happens in Hawaiian Islands, you get a pulse that elevates the whole terrain, 3,000-4,000 feet. And then once that heat source goes away, the whole land sinks again. And it changes the drainages quite a bit, the paleo drainages of these streams. But that's a fascinating topic unto itself. Again, these are all the calderas coming into Yellowstone up here on the right-hand side. Again, there's lots going on in Yellowstone, as we know. I'm one of the geologists that don't expect a supervolcano to erupt in our lifetime, but Scott might have a different opinion here. But anyway, that's what Yellowstone looks like. We talked about it, the magma chamber there underneath the Yellowstone. What caused Yellowstone, again, very similar to what happened at Crater Lake in terms of production. The ash cloud from Yellowstone covered pretty much most of the United States. Quite a bit of ash everywhere. Again, that's a lot going on in Yellowstone right now. They just had to reconfigure the walkways there at Norris Geyser Basin because the magma keeps moving around. Norris Geyser Basin's over here by the cursor here. And with that, I'll turn it over to Sylvia, and I guess however you want to conduct questions, Sylvia. Well, that's me. That's me and my my grandkids here. We got Yellowstone and we got Smith Rocks there.
All right. If you'd like to stop screen sharing, there we go. We can do this. So from John Boyd to everyone, thank you. So if we have questions, you can either type them in the chat or you can raise your hand with the little reactions down below. Or if we don't have too many people at once, we can try just having someone ask a question, unmute and ask your question and then remute. From Tom to everyone, thanks, Bill.
Okay.
Suki. So the silica hotspot is the Yellowstone hotspot.
Well, what geysers create is something called sinter, and that sinter is basically a silica type of deposit, and the eruption there is because the crust is so thick at Yellowstone. Most of what comes out of Yellowstone is rhyolitic or highly silicic. That part is true. All that Huckleberry Ridge formation that surrounds Yellowstone, we're talking 600-700 feet of ash that came down. That's all rhyolitic or all highly silicic. So that part is true, yes.
Okay. Do we have any other questions? Here's one from Marilee. Did you say, whoop, now they're coming in here. Let me go back to that. Did you say that you take people on tours of the Elk Rock area?
Oh, we could. We could certainly arrange that. I'm game, Sylvia. Whatever people like to do, a short field trip out there would be fine in my opinion. Sure.
Mm-hmm. Okay, from David Lewis, what causes the hotspot?
So that's pretty much unknown, Dave. I mean, there's the ideas that range between the Earth getting smacked by a rather large meteorite is one of them, where the meteorite is strong enough to break through the crust and into the mantle. That causes a disturbance down in the mantle. They're just now getting into looking at, there's a science called tomography where they basically use the refraction of the if you have an earthquake, you can use the earthquake to measure different densities of some of the substrate in the mantle. And so you can kind of get a shape for all the weirdnesses and all the shapes that are down there. And because we can't see it, we're just learning how that works. The mantle hotspot, it falls into that category. I mean, we've got one at Yellowstone, and we've got one in that's, basically it's right now active in Iceland. That one is producing a lot of basalt right now, for instance. That's all basaltic. If you guys get a chance to look on the YouTube, that's a fascinating eruption. Very similar to what happens at Kilauea in terms of all being basaltic, which is very low in silica, by the way. But to answer your question, Dave, I don't know that anybody truly understands what the origin of these mantle plumes. What is important is they tend to stick around. And, here in the last 50 million years, I just ran about 6 or 8 different major concepts Maya, and that hotspot continues. The hotspot is right now, and one of the reasons it's very silicic in the United States is because we went from about 30,000 foot of mantle in Idaho, and then you get into Wyoming and Montana, the crust is 45 to 50,000 feet thick. So there's a lot more continental crust that's got to bubble through. And so that may be, it may do something to this mantle plume that we don't quite understand. So stay tuned. We have the Geological Society of America meeting in Oregon, and they like to meet in Oregon because there's so much geologically happening in Oregon. So it's something to stay tuned, and that happens down there at the convention center in in
October.
Yeah, thank you.
Suki, when she asked her question, she said, no, the Celestia. I wonder if she was talking about the Celestia or
Oh,
something.
Celestia.
Yeah.
Oh, I'm sorry.
Hotspot became the Yellowstone hotspot, question mark.
Oh, okay. I'm sorry. I misunderstood. Let's see. Oh, so yeah, the Celestia hotspot did become the Yellowstone. I never did say that, but yeah, what formed Celestia, and it's a mantle hotspot. And again, because it didn't bubble through any crust, so to speak, the mantle hotspot out to sea, as it bubbled up through the oceanic plate, it produced only basalt. And then once it docked into the U.S., and the first few eruptions it had, it's only going to produce basalt. But if you go to Smith Rocks and look at the Crooked River caldera, there's very little basalt there. And the difference being is now the hotspot, it's still producing the heat, but now it's got to bubble up through 30,000 foot of continent. And the product of that interaction of the basalt with the country rock, as we say, produces rhyolitic. I got confused with the words silica, but it's the terrain that docked with us is called Celestia, and it refers to the Celets Native Americans that live on the coast of Oregon. And so that's how that got its name. It has nothing to do with the minerals silica. My mistake.
Okay, Larry asked, what caused the Columbia River basalt flows to occur in that place at that time when the flows didn't happen otherwise?
Yeah, that's a perfect question. And again, when you have, basically, you don't get flood basalts unless you have terrain that's basically in tension. Basically, it's opening up. And so what happened, if I could go back to that, or maybe I'll try to explain it with my hands, but you have the plate here, and it's basically, it's under compression. And when this thing burns through, the hotspot burns through, it basically releases all that tension or compression that you're having, and suddenly you have a lot of material that's lighter than the mantle, and it's all basically going up into an area that's opened up. So you got about 5 things going on all at once. You don't get a lot of flood basalts anywhere in the world. There's only 3 or 4 major large igneous provinces. There's one in Siberia, which is the largest. There's one down by the Deccan LIP over by Mumbai, and then this Columbia River basalts that's right outside your doorstep. But the combination of, you have to have 3 or 4 different combinations, and that's exactly what we had when you had the relaxation of the crust, with a lot of material being melted from that plate, which is lighter than the mantle. So all of a sudden you had all this material that had to get up and out, and it just basically oozed up out of basically these vents in the they start down by John Day in that area, and they migrate up towards north of Pasco is where the most recent ones are. And that occupied a time from about 16.8 million years ago, and then basically the whole episode of the Columbia River basalts was over by about 12 million years ago. So, and the most voluminous that occurred was the Grand Ronde basalt, and that was between about 16.4 and 16.0. About a 400,000 year period where 80% of the Columbia River basalts flowed onto our landscape all the way out to sea, out at Tillamook and down by Cape Falcon. I don't know the name of that.
Keith said, thanks for a great talk. You wove together many pieces of my Northwest geology information that I heard before. You put it into a coherent framework. Well done.
Well, thank you.
Marilee said, how would I arrange to go on a tour of the Elk Rock area?
If you got my email at the end, I mean, that would be the best way. And Sylvia and Rick, if you have anybody that contacts you, I mean, I'm happy to pick a time and date and go out there. You know, I do it for railroad stuff. I can do it for this.
All right. Catherine says, I think okay. I think the question is Celestia, the subducted Iceland off the Oregon coast, the same hotspot that's now under Yellowstone.
Yeah.
So she was putting that in. Thank you. Jean says, connection between spreading ridge and hotspot, question mark?
Yeah, that's a great question too. And that's you know, if you look at, if you go on Google Earth or Google and just type in Icelandic hotspot or Celestia hotspot, you'll pick up some diagrams that show exactly that. You've got a combination of a spreading center with a hotspot, and that's one of those mysteries. You know, nobody has really quite figured that out. So, Gene, I would, you know, why don't you stay tuned and when I figure all that out, I'll talk to Sylvia and we'll get another talk going. But I don't know that unless somebody in the audience knows that answer. I know it's happened more than once, so there must be. Again, you have a convection going up with the spreading center, but you know, the hotspot seems to be somewhat unique in itself. And if you look at the whole mid-Atlantic spreading center, which goes from way up north of Greenland all the way down through to Antarctica. I mean, it's the whole length of the you know, between the eastern and western hemispheres. There's only a couple spots, Iceland being one of them, where you have a significant land. So, you know, I don't know that people quite understand the relationship between a spreading center and a hotspot. I'll keep working on that, Gene, and try to get something back to Sylvia. If you got my email, I'll dig in that. I'll dig into that subject a little deeper as well.
And Nicole says the correct spelling for Celestia is Siletzia. So for those of you who wanted to Google and look at that, David Lewis says, thanks. Lawrence asked, you showed several hotspots in Oregon. Are they all the result of a single hotspot?
Yes. And I tried to use the analogy that if you look at the Hawaiian Islands, you know, it's not, you know, basically what happens, the hotspot starts burning through the mantle, or through the oceanic crust, I should say. And all right, so it starts bubble up, you know, in this case, the Hawaiian Islands, it starts building an island. Well, the plate keeps moving, the lithosphere, the oceanic bottom keeps migrating to the west, because the hotspot's already established a route for its magma to go. It's easier just to keep following that magma chamber all the way, as it tends to migrate from east to west. You follow me? So the stuff comes up and it starts going over there, and basically the magma will follow the plate over until such time it can't, and then it'll snap over. So what will happen, it'll form an island here, and then there'll be a gap and it'll form another island. And we see that pattern everywhere of a hotspot that's migrating over or under a lithosphere. It'll jump like that. So it's just the one hotspot, and those dots that I showed in Oregon, are replicated down through Idaho with those patterns of calderas, all that stretch from one end to the other and through south along the Snake River Plain through there. You know, the only difference being is that chain of volcanoes would have extended from Yellowstone right out to sea at Mendocino, but for the fact that the ones between the Nevada state line and the California coast basically got translated up into where we live now, up in Portland.
Nancy and Kevin say, thanks, Bill. Great presentation.
All right. Good to see you guys.
All right. Well, thank you so very much, Bill. All right. Well, thank you everyone for coming tonight. And like I say, we will have this lecture by Bill. Thank you so much, Bill, for being our speaker tonight. And that should be up next week. And then I'll be sending a notice next month letting you know what program we'll be having then. Thank you for joining us.
All right. Thanks, Sylvia.
Good night. Thank you.